Hi all, welcome to a new video lecture on the course Algorithm Analysis and Design. So here we will discuss something a basic classification of algorithm design, that is iterative and recursive ways of solving a problem. Okay, so let me write like this: algorithm design we can do in two different ways. Like one way is iterative algorithm or iterative way of solving problem, and another one is recursive algorithm. Okay, recursive algorithm. So we will see that it is something we all are familiar with. Like fundamentally, when you observe the algorithm, that you know already, you can see that some are iterative in nature and some are recursive in nature, right? So iterative is sometimes known to be the top down approach or top down design, and recursive is known to be bottom up. Now the question is it possible for us to come up with a iterative as well as recursive algorithm for every problem, or whether they are of so for certain problem it's only possible for us to come up with iterative algorithm. It's not like recursive, it's difficult, or sometimes recursion will work and other will not work. But the thing is that for every iterative approach, there is an equivalent recursive algorithm, and vice versa. So you can keep it as a point. Okay, now we can also think of a question like which of the two is efficient. Okay, but we are not looking at this parameter at this point. So sometimes this iterative way, okay, anyway, the notion of efficiency we will see later. Okay, so how to understand this efficiency, you have to analyze algorithms. So how to analyze recursive as well as iterative algorithms we will see later. Okay, so now in this video my intention is to introduce you these two approaches or ways of solving an algorithm. Okay, so let me take few examples also. The first one is factorial. Okay, so given a number, how to find out its factorial? As you already know, one way is like you just keep on multiplying, like 1 into 2, then you multiply the next number, and then you multiply with 4. Like that you will proceed, and finally 1 into 2 into 3 into 4 into etc into n will give you the factorial of n. So this is one way of doing, and another one is you can proceed in a bottom up manner. Like you are starting with this n, then n multiplied with the n minus 1, then n multiplied with the n minus 1, further multiplied with the n minus 2, and you can keep doing like that. And this is also a way of doing factorial, right? Finally something like 2 into 1 finally. So that about it. So the first approach is what we call as the top down approach, right? So this is your top down approach. This is your bottom up approach. Yeah, so if you want to write an algorithm for this, something you already know, you can use a variable like fact, and you can initialize it with 1, then some for loop you can write down. Okay, and this loop is going from I equal to 2 to some n, and in every iteration you are updating the variable fact by multiplying the variable fact with this particular I. And finally this variable fact is supposed to contain d factorial of the given number. So here this things should be written inside a function. I am just writing the pseudocode only. Okay, and similarly here how to do that? Okay, so let me write as a recursive function. You have factorial of n, and inside it you have to verify that base condition, right? So when you write any recursive program, this is very important, when to terminate it. If this is the case, then you can return 1. Okay, now Otherwise you can return something like n into fact of n minus 1 that you can recursively call. Yeah, that about it. So this is two ways of doing the problem, and the top down approach and the bottom up approach for solving the same problem. Now let's take another example. So another fundamental example, that is this Fibonacci series, right? Do you know how to start the series? It depends. Suppose say I am starting like 1 1, then 1 plus 1 2, 1 then 3, then 5, then 5 plus 3 11, sorry 5 plus 3 8, then 13, then 13 plus 8 21, like that it is proceeding, right? So this kind of a series that you all are knowing already, and now you can easily write the iterative as well as a recursive approach. So how will you write that iterative way? Systematically you start from the first element, keep on printing. So you can initialize a variable a and another variable b, say both with 1, so that is our first. So then you can print this a and b, right? At every iteration you can print. Okay, if you want you can do this. Yeah, no problem, you can print at this point, print a comma b. Then you have a for loop for I equal to 2 to n. Assume that the first two iterations were over, and in every iteration you can calculate say in a third variable you can add this a and b, and then you can update the variable, say a with b and b with c. Okay, and you can just print the c also, that you can print at any point. Okay, fine, something like this. So this will work, and this is the top down approach, right, for solving the problem. Now what about the bottom up way? So I can write a recursive function, say Fibonacci of n. So then inside it you can think about the base condition always. So if n is equal to 0, so because here I assume that this is a 0th Fibonacci number, and this is the first Fibonacci number, this is the second Fibonacci number, this is the third Fibonacci number, this is the fourth one, like that. So this is how I am giving the indexing. Okay, so this is my indexing. That's why the if n I am passing a 0 means I want the 0th Fibonacci number, which is 1, or if n is equal to 1. So these are all my basic assumptions. If you want you can assume differently also. Then you are supposed to return 1. Fine. Now I just, so here I am focusing like I want the nth Fibonacci number. Every iteration, maybe by running a simple for loop you can call it and you can print it. Okay, so like that. So this will just give you the nth Fibonacci number only. So if it is 0th or 1th Fibonacci number you are asking, it will return you 1. Otherwise it will return recursively Fibonacci of n minus 1 and Fibonacci of n minus 2. The it's going back and it's taking these two. Okay, so that about it. Now let me just show you how this recursive procedure is working. So in this example itself, if suppose I am calling something called as a, let me write it like a fact. Okay, fact of 4. So what is happening is from this factorial function, maybe you may be calling it from main and all. So it will just take and it will check whether this n is equal to 1. It is not 1, right? So it will be returning something like n into fact of 3, like that. So from here it will call further. So n, what is your n? N is 4, right? So it will do like a 3 into fact of 2. At this point again it will do like a 2 into, it recursively calls fact of 1. Okay, so at this point when n is equal to 1, it will be it will return 1. Okay, so that 1 will come. Now this computation will be over, and 2 into 1, so that result 2 will come here, and 3 into 2, so this will be like a let me show that backward path using a different color. So when you are calling factorial 1, immediately it will see that this n is equal to 1. So this is true, right? So it will return 1. So that one will come here. So 1. Now at this point this process is over, this computation is over, like a 2 into 1. So this will return 2 into 1, that result, that is 2. So here at this point 3 into 2 is finished and 6 will be written, and here it will return 4 into 6 like 24. And you know that like at every time when you are calling the same function again and again, we call like a new activation for the same function begins, and it will create something called as an activation record. So first it will create the activation record of factorial 4, and that will be pushed. So with the help of stack this execution is happening, right? So hope you know this from other system software related courses. Hope you got an idea about this already. Anyway, otherwise you can clarify from the class if you are having any confusion on it. Okay, so then from this it will recursively call factorial of 3 and factorial of, so like that it will take some space. So that is one problem with this recursive procedure. But if you are looking at iterative procedure, it's space efficient, means this extra stack space is not there. So for just for supporting this recursion, basic recursion itself, I need this stack. So now when this factorial 1 returns, this activation record will be popped out. So till that when all are active, this means space it will consume. Okay, so that is how we are tracking it. And why we are using stack, it is because factorial 4 is the first activated function and this is the last activated function. You can see that it is the last activated function is getting deactivated first. So it is following that last in first order, or the first activated function is getting deactivated last, right? So that is why we are using stack as a data structure to implement this concept. Anyway, I hope you have this feel already, this how this recursion is proceeding. So or let me take this example also. So here if you are taking a small example, like suppose I want to know what is Fibonacci of 4, you know it, right? It's the fourth Fibonacci number. So what I will be doing is I will recursively, so n is equal to 0 and 1, that condition fails, so it will recursively calls this Fibonacci, this particular function for 3 and Fibonacci of 2, like that. So once this 3 and 2 finishes, it will try to add these two and the result will be returned back. Okay, so but that recursive call will be happening like this. So Fibonacci 3, again it will call Fibonacci of 2 and Fibonacci series, I mean Fibonacci number, first Fibonacci number, and here it will call for the Fibonacci of first Fibonacci number and Fibonacci of 0th Fibonacci number, right? So after some day, so this is in this way it will be proceeding. And now let me tell you, so whenever you are reaching this point, okay, so this Fibonacci of 1 or Fibonacci of 0, they are base conditions, right? So 0th Fibonacci number or 1th Fibonacci number, it is 1. So what is going to happen? So this will this particular recursive call bottoms out, right? So it will return a value 1 and this will also return a value 1, and finally this addition will happen, right? And that value will come here. So here you will get a value of 2 for Fibonacci of 2. And similarly when you are calling Fibonacci of 1, this is this base condition now, right? So it is returning value 1, and finally these two will be added by this these two, I mean Fibonacci 3 call, and it will calculate the sum or the third Fibonacci number as 3. Okay, so that will happen. Now when to proceed it further, we need Fibonacci of 2 also, and that time it will further it don't know, right? So it will calculate this Fibonacci of 1 and Fibonacci of 0, and again you know this will be giving 1, this will be giving 1, and this will calculate this 2, and finally these two will be added up, and so that you will get the fourth Fibonacci number as 5. So here you will get 5, and you know the procedure and how this stack, every time whenever you are having a new recursive call or activation of a function, some stack space will be created and it will keep on the activation record and this processing everything. That idea you are already having. Now the question is so here you can observe something interesting, what I can tell you. So this Fibonacci of 2, right? So you know the difficulty, like this, how this Fibonacci, this particular recursive sub problem is doing this task, like it is calling Fibonacci 1 0 and they are adding these two things together. And similarly the same task is getting repeated here, right? For this kind of a small problem, the same task and same result, the same right. but why we have to do the computation again and again? So is whether it says that recursion is doing some more tasks than the iterative procedure. We feel like that, right? Because iterative is very straightforward, one after another we will keep on adding and we are finding out whatever things we want. So here I am trying to print all the Fibonacci numbers, but here I am finding the end one. So this also you can modify like that. Okay, so if we are writing a function to find the end Fibonacci number, like that, finally you return that C. So that is a logic, like that you can update it and you can do this checking and all. Okay, anyway, so you got the idea, right? So now the question is, this Fibonacci call is repeatedly calculating. So whether it says that this recursive function is doing something more like that. So this kind of this computation structure which I drawn here is typically known to be the recursion tree, by which one can analyze how a particular recursive function is evaluated. So the observation is like the Fibonacci 2 is getting is evaluated 2 times. Okay, so is it something needed for us? Really, is it needed? Okay, so that about it. So if you are looking at some bigger number, definitely many such repetitions you can expect at this point, right? So if you want to find out Fibonacci 4, fifth Fibonacci number, see Fibonacci 4 you will call and 3 will call, and that 3 and this 3 whole thing will repeat like that many times. This repetition thing you can see. So the question is, are we doing more work here? More work, say when it comes to recursive procedure over iterative procedure. So what you feel at this point? So definitely the answer is yes, right? Yes. So that is what we saw it. Or so now the thing is that what about but even though we are doing more tasks, we have a systematic or a very nice way by which we can save this time. So we don't have to repeatedly evaluate all this problem again and again. But the basic form of recursive procedure, it will do that. Okay, but we actually don't want it. We can improve it by a very slight adjustment to this one. Okay, so a variation of algorithm design technique called dynamic programming, we will be studying it at some later point, and there we are actually so that dynamic programming, how that technique is efficient is because it's saving this time. Okay, so it's not going to repeatedly calculate this Fibonacci of 2 times. Okay, so it will save that. So like that, for some bigger input, it will save a lot of time for you. Okay, so that concept we will study later, but at this point something like this you can think of as a negative side of the recursive problem, and not with all problem, but here you can see that. And also here the another concern we are having is the stack space. Okay, so there is something I mentioned here. So the stack space leads to the more space requirement for recursive approach than the iterative approach. Okay, so this leads to something called space complexity. More complex space requirement is needed for it. Okay, anyway, so you got a feel about it. So what we are trying to say is the two major classification, how we can solve a given problem. One thing is you can think about an iterative way of doing it or a recursive procedure. So you can call it as top down and bottom up procedure if you want, and you can see that for every iterative approach there is a equivalent recursive algorithm also. So you can't say that one is more powerful than the other one. But what about the efficiency notion? So here we saw that the one is recursion is found to take more space, as well as it's doing some computation repeatedly. So iterative is found to be better, but it is not like that. We have ways by which we can make this recursive procedure better. Okay, and sometimes it's always easy for us to think the recursive algorithm for most of the problem than the iterative way, but it is not like that. Both are of same power. For every problem you can have this recursive and iterative version in that, but still this way, the when you are looking at the programs, you will get a very with some few steps you will be doing it. So here itself you can see that. Okay, so it's always the default thinking procedure according to me, it is recursive. Okay, so that about it. Yeah, thanks for watching.